For today's lab, we will be discussing about two techniques that we can use to separate and then analyze a mixture of two liquids. To separate the components of the liquid-liquid mixture, we are going to use Hickman-Still distillation, and then to analyze how successful our separation through distillation was, we are going to analyze the separated components using gas chromatography. Hickman-Still distillation is based on separating two or more liquids in a mixture depending on their boiling points. For our experiment today, we're going to use a liquid mixture prepared by mixing hexane and toluene. Based on what we learned in the previous class, both of these compounds are nonpolar, therefore they are miscible with each other. The boiling point of hexane is 69 degrees Celsius and the boiling point of toluene is 110.6 degrees Celsius. And I'm going to use red color to indicate hexane and green to indicate toluene, so it's easier to kind of visualize what is happening during these techniques. When we continuously supply heat to this mixture of hexane and toluene, that is in a distillation apparatus, the hexane, because it has the lower boiling point, is first going to start to separate from the mixture near the temperature to its boiling point. And because the boiling points of hexane and toluene are considerably apart, we are able to separate them into their individual components. However, this technique is successful only when there is a large difference in the boiling points of the components in the liquid mixture. What do you understand when we say boiling point? If we have a liquid in a closed system and we supply heat to this liquid molecules will start to evaporate and form vapor or gas molecules. As we continue to supply heat more and more, liquid molecules will turn into gas molecules. These gas molecules can exert some pressure. Like, for example, when we blow into a balloon, the balloon expands due to the pressure from the gas molecules, right? So all the gas or vapor molecules have a pressure which we call as the vapor pressure. When this vapor pressure equals the atmospheric pressure, the corresponding liquid starts to boil. So the boiling point is the temperature when the vapor pressure of a liquid is equal to the atmospheric pressure. Now let's take a look at how Hickman-Still distillation works. First of all, here's how we set up the apparatus. There is the hot plate, and this is the 5 ml vial where we will have our liquid mixture, and that is fixed to this piece of glassware that we call a Hickman-Still, and it has this stem part and this larger bulb kind of part, and there's this little side arm with the cap, and there are some grooves made into this glassware so small amounts of liquid can be held in these grooves. The inside of the Hickman-Still is hollow, so we can place a thermometer across it, and to help place the thermometer we can use this glassware called thermometer adapter and an O-ring, which is a very thick rubber band kind of thing. So we use them to help place the thermometer across the Hickman-Still. And it is very important to have the thermometer bulb placed just below these grooves of the Hickman still, and that is because we are able to measure the accurate temperature of the hot vapors by placing the thermometer bulb at that position. So when we supply heat, if this is our liquid mixture, it will start to turn into vapor, and those hot vapors will start to rise across the stem and reach the bulb part of the Hickman still. And you can see the thermometer bulb is directly coming into contact with the hot vapor. So it's measuring the temperature of this hot vapor throughout the distillation process. Once these hot vapor reach this bulb part, the heat from those vapor molecules is diffused to the surrounding air, and that causes those vapor molecules to cool down and condense, form little droplets, and those droplets would fall down across the glass wall and collect in those little groovy area. We keep supplying heat until all of the liquid at a particular boiling point has collected here as a liquid. And this liquid that has been distilled out of the mixture, we call it a distillate. We can take off this little cap, insert a glass pipette inside, and draw out this distillate and store it in a separate vial. If this mixture had multiple components of liquids, then we can distill multiple times and collect several distillates that we can label as different fractions, different distillated fractions. For 100% successful separation of liquid components in a liquid-liquid mixture, they should have at least 100 degrees Celsius difference in their individual boiling points, between their individual boiling point. But to obtain at least a partially successful separation of liquid components in a liquid-liquid mixture, we should at least have boiling points of those components 50 degrees apart in the least. The two liquids we're using for this lab is hexane and toluene, right? And hexane has a boiling point of 69 degrees Celsius. Toluene has a boiling point of 110.6 degrees Celsius. So they're at least 50 degrees apart in their boiling points, so we'll be able to see a somewhat successful separation of hexane from toluene from the mixture. I'm going to use red to indicate hexane and green to indicate toluene. When I say the boiling point of hexane is 69 Celsius, what does that mean? Based on what we learned earlier about the boiling point, that means hexane liquid turns into vapor much faster compared to toluene, right? That means the vapor pressure of hexane equals the atmospheric pressure at 69 Celsius, while the vapor pressure of toluene equals 1 atmospheric pressure at 110.6 degrees Celsius. So hexane will turn into vapor when we first start to supply heat. And as more and more the temperature comes close to 69 degrees, most of the hexane liquid will start to actively boil and convert into hot hexane vapor. And you can see our thermometer bulb is directly measuring the temperature of those hot vapors. And once they reach the bulb of the Hickman still, the heat will be diffused to the air, and these vapor will form into condensates, and those condensates will collect at this groove part, and we can open this cap, insert a glass pipette, and draw out this distillate of hexane and store it in a separate vial. Once we continue to supply heat, and the temperature goes above 69 Celsius, all of the hexane in this mixture is boiled and removed from this mixture. So there will be no more hexane vapor collecting on this stem part. So although we're supplying heat, the thermometer is suddenly experiencing a lack of hot vapors around it, so the temperature reading is actually going to show a temperature below 69 once all of the hexane has been removed. And then until it starts to get closer and closer to the boiling point of 110.6 Celsius, the temperature will be kind of low until the toluene starts to vaporize, and that's when the thermometer bulb will start detecting hot vapor again, and the temperature reading will start to go up. So we're going to look at the temperature change versus time for this experiment in a later slide, and that will help you to understand more what happens during this experiment. So eventually we collect the first distillate, which should be mostly hexane, which we label as fraction 1, and once we let it continue to heat up to 90 degrees, and that makes sure that most of the hexane is eliminated from the system, and all that is left is toluene, and we will consider that as our second fraction. Okay, so here we have the temperature recorded every 2 minutes, and you will be getting this data in your lab report guide, and you are asked to plot a graph where you plot temperature in y-axis against time in x-axis, and you're going to observe how the temperature changes throughout this distillation experiment to separate hexane and toluene. So you can see up to like 12 minutes there is no change in temperature, and as we continue to supply heat, now the temperature starts to rapidly increase as hexane is turning into hot vapor. And at this time point, which is around 22 minutes, we can see that 72 degrees Celsius, it's very close to the boiling point of hexane. Hexane is actively boiling now. And for the next several minutes, we don't really see much of a change in the temperature. Why is this? So let's take water as an example. When we're boiling water, the temperature of the boiling water is 100 Celsius. And the temperature of the boiling steam our vapor is also 100 Celsius. So as long as this water is boiling, all the heat that we provide is used to convert the liquid into vapor. So overall, we see as if there is no temperature change happening, because as long as this is boiling, the next heat that we supply is used up in this phase conversion from liquid to vapor. So if we were measuring the temperature with the thermometer feels like there is no temperature change happening. So while all the hexane actively boils, we do not observe a temperature change in the thermometer. Once all those hot hexane vapor is removed from the system, it's going to take some more time until the temperature or the heat can allow the temperature to increase back. What I'm trying to say is it's going to take some more heat to convert toluene into vapor, because toluene's boiling point is much higher. So it's going to be a while until the hot toluene vapors reach the thermometer bulb, right? So temporarily, the thermometer bulb does not have any hot vapor around it. So that's why we see a decrease in temperature in the next several minutes. And as more time passes and the temperature starts to increase again, that means toluene is now making hot vapor. And if we continue to heat this all the way up to the boiling point of toluene, then toluene would start to actively boil, and while toluene is boiling, you would see the temperature stay constant around this temperature, and then the temperature will again go down. So this is what you would observe for the temperature change for this experiment for separating hexane and toluene via distillation. So you'll only get data up to like 40 minutes, I think. But I added these extra minutes with some extra data points to show you how it can decrease, and then it can start increasing again as toluene starts to turn into vapor. So you're going to get this data in your lab report guide, and you can use Excel, or you could do a hand-drawn graph if you like to plot temperature versus time, and you can observe these changes in temperature as each of these liquids separate via distillation. Next, we're going to look at gas chromatography, because those two fractions that we collected, we are going to run them through a gas chromatogram and see how successful our distillations were. Were we able to 100% purify hexane? Were we able to 100% purify toluene? So our expectation is, since this is a partially successful distillation, we expect some little amount of toluene to be present in the first fraction that contains mostly hexane. So here's a picture of a gas chromatogram, and this technique is generally used to purify, separate, or analyze organic compounds that can be vaporized without decomposing. So we need to convert these samples, we turn them into vapor at a very high temperature. So it's important that these compounds do not decompose at those high temperatures to be able to be used in gas chromatography. In gas chromatography, compounds in a mixture get separated between a mobile gas phase and a stationary liquid phase. This means there is a liquid component that stays in place while a gas phase passes along that liquid phase carrying our compounds that needs to be separated or analyzed. This separation of compounds between the mobile phase and the stationary liquid phase depends on characteristics of the compounds such as their boiling points or their polarity. Now let's take a look at how the inside of the gas chromatogram works. So first we have a gas tank that contains the carrier gas, and this gas is inserted into the machine at a certain pressure, and in a mixing chamber the gas gets mixed with our sample, which is injected through a syringe through this injector port, and the oven in the gas chromatogram heats this mixture, convert them into vapor, and that vapor is pushed at a high pressure through this column. And as the mixture moves through the column, the molecules will get separated into their individual components, and they will exit the column at the end of the column, or we call it eluted from the column at separate times. And a detector is present at the end to recognize the compounds that are exiting or eluding the column, and also to detect how much of that compound was present, and it will generate data in a graph form, which we will see in the computer. And this graph is time versus signal, and as each compound exits the column, we get a peak at that specific time point, and the size of the signal is directly proportional to how much of that compound was present in the original mixture. Let's take a look at how the inside of the column is like. So we're basically going to look at a cross-section of the column. So here it looks like a thin tube, and it's packed with beads that are coated with a liquid. So that is going to serve as our stationary phase. So these solid beads are just there as a solid support, and around those solid supports there are these liquid layers, and this is what is packed in the column. And this doesn't move, so we call it the stationary phase. The carrier gas is going to pass through these column beads coated with liquid, so it's moving, so we call it the mobile phase. And the carrier gas can carry the molecules that we want to analyze through this column, and as they pass along this column, they will get separated either based on their boiling point or their differences in polarity. So just for this lab, let's assume that this liquid coated on these beads are non-polar. So this column is non-polar. The column that we're using for this lab is non-polar. And let's also assume the compounds we're trying to separate are also non-polar because hexane and toluene are both non-polar. And that means their separation will be solely based on the differences in their boiling points. Unlike in Hickman-Still distillation, we don't need large differences between the boiling points. Even if they're just 1 degree apart, the gas chromatogram is sensitive enough to detect them separately. So just as an example, let's say we have this mixture of orange, blue, and green molecules, a mixture of it, and let's say the orange molecule's boiling point is 50 degrees Celsius. The boiling point of the blue molecule is 80 degrees Celsius, and the boiling point of the green molecules are 100 degrees Celsius. They're injected into the column as a mixture, but as they move along the column, since the orange molecule has the lowest boiling point, that means it exists more as a vapor than in liquid. So it exists more in the gas phase or the mobile phase. That means it will move faster with that mobile phase and reach the end of the column much faster than the blue and green molecules. That means it gets separated from the other two compounds. Then the blue molecule has a lower boiling point than the green molecule, but it's higher than the orange molecule. So some of it is going to exist in the vapor phase, while some of it gets dissolved in the liquid phase as it moves along. So it gets kind of slowed down as it moves through the column and it gets separated from the orange molecules. Since the green molecules have the highest boiling point, they will mix with the liquid even more compared to the blue molecules, so they will get even more slowed down and they will exit the column even after the blue molecule has exited. So if we drew the graph that we're expecting for time in minutes, where's the signal? Here's the baseline. We will first see the orange molecule exit the column. Then we'll see the blue molecule exit the column. And then we'll see the green molecule exit the column. And these specific times that they exit the column are called the retention time. How long they got slowed down, or how much they were retentioned inside the column based on the time they came up. So the green molecule was slowed down or held back or retarded the most, so it will have a higher retention time, and the orange molecule that exits first will have a lower retention time. And the size of the signal is directly proportional to how much of that compound existed in the original mixture. Since we have about an equal mixture of orange, blue, and green, we should expect signals that are about the same size. Now, if we apply what we learned in the previous slide to our experiment of separating hexane and toluene, remember the two fractions that we collected through Hickman-Still distillation? Fraction 1 would contain mostly hexane and maybe a little bit of toluene, because a little bit of toluene might have started to evaporate by the time hexane was boiling. But fraction 2 should mostly contain only toluene. To analyze how good our distillation was, we're going to pass each fraction through the column and get a graph to see how they look like. So if we passed fraction 1 through the column, and again assume that this column is nonpolar, and hexane and toluene are both nonpolar, so the factor that decides how they get separated in the column is going to be their boiling points. Since hexane has a lower boiling point, it's going to be present in the vapor as a vapor more than mixed with these liquid layers, so it's going to move faster with the mobile phase, and it will exit or elute out of the column at an earlier time point. So to get the retention time for your compound, you should draw a line from the point of the peak perpendicular to this baseline and the x-axis, and where it meets the x-axis, that is the retention time for hexane. So this is the peak for hexane, and then after a while we get the peak for toluene because it's slowed down in the column because it has a higher boiling point. And since we expect more hexane to be present in fraction 1, we should see a larger peak for hexane and a very small peak for toluene. If for some reason we had a large peak for toluene in fraction 1, that tells us that we didn't do our distillation properly. In fraction 2, we expect it to mostly be toluene, so the graph we get from that, we should expect not to see any peak for hexane, but a very large peak for toluene, and the retention time, let's say this is retention time of toluene, let's assume it was 5 minutes here. It's going to be the exact same time that it elutes in the second graph as well. So this is kind of like a reference point. So if somebody in Australia, let's say, is doing a gas chromatogram to separate a hexane and toluene mixture, and they're using the same settings in the gas chromatogram, and they're using the same temperature settings and everything, and they try to separate toluene, toluene will always come out at the 5-minute time point. So it's kind of like a standard. If all the other conditions are the same, then the retention time is going to be like a constant or a standard factor that you can relate to toluene specifically. So this is what we hope to see in our results for fraction 1 graph. So for fraction 1 graph, we expect to see a lot of hexane, a little bit of toluene maybe. For fraction 2, we expect to see a lot of toluene and almost little to no hexane. And you're supposed to break out these retention times for each peak And in the next slide, I'm going to show you how we get the composition of each of these compounds in the mixture by calculating the area under these peaks. The area under the peak is directly proportional to the amount of that compound present in the mixture or fraction. So let's say we are analyzing a fraction that contains both hexane and toluene. This is just as an example. And how would we calculate the area under the peak? So for example, we're looking at this toluene peak. We get the height from the baseline. Remember, it's not from the x-axis, it's from the baseline. Height from the baseline to the top of the peak. We measure that. And then at the we get the width at half height. So let's say the height here was 4 centimeters. Then half height would be 2 centimeters, right? So let's say this is 2 centimeters and we get the width of the peak at half height. So in this example at 2 centimeters. So we measure the width at half height. Let's say, for example, the width was 1 centimeter. The area under the peak would be height times the width that we measured at the half height position. So it's 4 times 1 squared centimeters, 4 square centimeters. So that's the area under this peak. And likewise, you can measure the height for this peak and then measure the width at half height point and also obtain the area under the peak for hexane. Then to get the total area, you add the area under hexane peak plus area under toluene peak. Since these areas under these peaks are directly proportional to how much of hexane or toluene was present in the mixture, we can use these numbers to calculate that. So the composition of hexane in the mixture would be area under hexane over total area times 100%. Composition of toluene in the mixture would be area under toluene over total area times 100%. And this way you can calculate the composition as a percentage and say, okay, 40% of hexane was present in this fraction, 60% of toluene was present in this fraction, something like that. So what we expect is to see a larger percentage of hexane in fraction 1 and a larger percentage of toluene in fraction 2. If you get that kind of numbers, then that means your separation went as we were expecting. If not, if there's a lot of toluene present in fraction 1, that means something was wrong with your distillation technique. Or if there was a lot of hexane present in the fraction 2, which is supposed to be mainly toluene, that means you did not either heat the mixture properly or it was never able to reach the boiling points of hexane. So this is the last slide. When you get the graphs for these two separate fractions, you might see that hexane has several peaks instead of just a single peak. So hexane can elute as several peaks instead of one peak. Why is this? That is because hexane solution is a mixture of its constitutional isomers. So here's hexane, the one that we are mainly focused on, but there can be other constitutional isomers, that is, other molecules that share the same molecular formula of hexane, C6H14, but their arrangement, the atomic arrangement, is different, or their spatial arrangement is different. So it could be a structural arrangement or spatial arrangement is different, but the molecular formula is same as hexane. So the hexane reagent that we use for the experiment can contain all of these constitutional isomers. And since their structures are a little bit different, and the structure plays a part in deciding what the boiling point of the molecule is, they have slightly different boiling points. And this causes the hexane to elute as separate peaks instead of one peak. So the constitutional isomers with the lower boiling points will constitute these earlier peaks, and probably hexane, the major one that we're looking at, is in these later peaks. So when you're having to calculate the area for hexane, you will have to calculate the areas under each of these peaks separately. You can label them 1, 2, 3, 4, and you will calculate the areas for each of these peaks separately, and to get the area of hexane, you will add the area for 1, area for 2, area for 3 with area for 4 to get the overall area for hexane. And some people might ask, like, so if we get this kind of separation, what are we going to record as the retention time? You can either choose to get 4 separate retention times based on the 4 separate peaks, or else you can get those 4 different retention times, add them all together, divide by 4 to get an average retention time instead of recording 4. So you can do either of that, that's fine. The main thing I wanted to explain was that because hexane is a mixture of constitutional isomers, it will elute as several different peaks than one big peak. That is all I wanted to discuss for the lab today. In the lab report guide, this time you will have to write the procedure. Make sure you write the procedure in past format, like you measured this much, you added this much, you observed this, or you recorded this. So it should be in the format that you did these steps. And for the data part, you will be provided with the 2 gas chromatograms for fraction 1 and fraction 2 analysis, and you are supposed to calculate the areas under the peaks and determine the composition of hexane and toluene in each fraction. And in the discussion, you should comment on whether your Hickman still distillation was successful or not, and what are the crucial points you should remember when designing a Hickman still distillation experiment, and what are things you need to watch out for, and how were these compounds separated through the gas chromatogram, because they were separated solely based on their boiling points, because they didn't have any differences in their polarity, right? So they were solely separated based on their boiling points. Try to explain what the retention time is, and try to explain how the composition can be determined by looking at the areas under the P. So you can make those kind of comments in the discussion.